Hi guys, a very good day to my lecturer Dr. Nur Alisa binti Ali. So today we are from group number 3. We're going to do presentation on our assignment group project 1. Our group number 3 we're going to do presentation on our assignment 1 from the subject of instrumentation and measurement. So before we're going to start our presentation, let me introduce all of my team members. So myself is Devananda, anak lelaki Murukapan. Number is B1224106007. My next member is Muhammad Harith. His metric number is B1224107488. And the last but not least, my next member is Amir Husni, B1224107757. So I'll be presenting task number 1, which is sensor selection and also principle. So for this task, I have chosen 3 types of sensor. Can you see over here? This is capacitive displacement sensor, IVDT sensor, and strain gauge sensor. Sorry, and the spelling should be GAUGE. So this is the picture that we have shown here. So as we know, capacitive displacement sensor is used to measure distance and also displacement. This is how to show how fast something can move. So the next sensor, if you see this capacity displacement sensors, actually it works like a capacitor. It's actually best for very small movement and also high precision. And if you can see the pros and cons, so as we know, the pros is very sensitive and accurate, and also the cons can be affected by humidity and also temperature. So the next one is LVDT sensor. So LVDT sensor stands for linear variable differential transformer. It is used to measure linear displacement, which is a straight line movement. So this is best for medium to large displacement, which is a very high reliability, and also normally most of the industrial used to use this for their measurement, as it is a very accurate and also very stable, and it's also a very long lifespan. And if you see the cons of keburukan of this sensor, it needs AC excitation and also signal conditioning. So the next sensor we have chosen is strain gauge sensor with whetstone bridge. So it used to measure strain, which is called stretching and also compression, which relates to force, load, pressure, and also bending. So then this is very best for using for measuring load, weight, and also force, like I said just now. But when you see the prawns, it's very accurate for high forces and high weight. But if you see the cons, it's very sensitive to the temperature. Okay, so the next slide will explain about capacitive displacement sensor. So the physical quantity measured for this sensor is actually displacement. Okay, it's actually displacement. So the displacement one, and also it measures small changes in distance between two plates. So if you can see, displacement is actually how much something has moved, and it also detects small changes between two plates, like any tiny movement or any vibration. The sensor classification, it is called passive sensor, but it still needs external power to work. This sensor measures changes in capacitance, which it explains the ability to store electric charge. As we can know, capacitance function is actually to store electric charge. So the next part, we're going to explain about the working principle. So as you know, the working principle, C is actually stands for capacitance, E is actually stands for epsilon, which is permittivity of material, how easily it allows electrical field line. A is actually stands for area of plates, and D is stands for distance between the plates. So as you can see, C is capacitance. So C is actually how much charge the plate can store. So then we're going to explain the working principle in our next slide. So this slide explains the first step is once the plate is fixed. So the next step is the other plates will move, which is connected to the object you wanted to measure. So the third one, when the object is moved, the gap changes. So the gap is what? The gap is D. So this is the gap. D is the distance. The fourth one is the changes of the capacitance. And the fifth part is where the change in capacitance is then converted into the electrical signal. So all is actually written in this formula. Okay. So this is the working principle we have explained for our capacitance sensor. So the next part we're going to go to LVDT, inductive variable displacement transducer can sensor. So as we know, this is a linear displacement because it measures straight line movement, means it explains how far an object moves in one direction. So when you see the sensor classification, it's a it's sorry it's actually a active sensor, not passive here, sorry. So this is active sensor. This sensor needs an external power to operate. As you know, it converts mechanical movement. Okay, it also converts mechanical movement into an electrical signal using the principle of electromagnetic function. So then later we will explain the working principle. So this is the working principle. We are just going to go through a bit. So this is an IVDT consists of primary coil and secondary coil. At the center position, the output voltage is zero, and when the core moves, it induces voltage changes, and the difference with the voltage between the secondary coil represent both magnitude. We're going to go through that the diagram. So this is the diagram of the working principle. So as you can see here, we have primary coil, and left and right we have secondary coil 1 and coil 2. Primary is in the center. So the primary coil is supplied with a constant AC voltage. So you can see the voltage of primary coil is being supplied by a AC voltage. So this will create an alternative magnetic field. So the next part is two secondary coil, which is at the left and the right side. So these are placed symmetrically on the both side of the primary coil. So this AC magnetic induces voltage into, which is V1 is coil 1 and this is V2 is coil 2. So if you ask about the movable coil, so once the core moves to the left, you can see the motion arrow. So once this moves to the core will move to the left and also will move to the right, and also its position will also changes how strongly the magnetic field links to the each secondary coil. So the next part we're going to explain about this right side of this diagram. So can you see this is the output? V out equals to V1 equals to V1 minus V2. You can see this is our V1 coil 1 minus with coil 2 to get the V out. So what will happen once the coil move? When the coil move, so when the coil is in center, the coupling is equal, and also V1 equals to V2. So V out is zero voltage because it's not moving, it's in null position. Means it's in stationary position. So this is means that they don't have displacement at stationary position. But when the core moves to the left, the core moves closer to core 1. Okay, move closer to core 1. So it moves to the left, it's more closer to coil number 1. So V1 is even greater than V2. So then your V out will become positive. So when the core moves to the right, you can see the core moves to the right, the core is closer to core number 2. V2 voltage, V2 is coil 2 is larger than coil 1, which is V1. So your V out is, it becomes negative. So then this is later your output will increase in the opposite direction. Okay, so this is some part that that I explained. Okay, so we have settled for that part for our working principle for LVDT. So next we're going to explain about stretch gauge with Whetstone bridge. So as we know, we are using physical quantity. Okay, this is physical quantity. We use strain, which is mechanical deformation, and the sensor classification is actually passive sensor because it requires an external excitation voltage. Okay, so this is the working principle for Whetstone bridge. Okay, so we're going to explain the working principle of this one lah. So this not so the accuracy of Western bridge relies on the whether it's a bridge or balance. We have two types, balance and unbalanced. So the balanced bridge is occur when this ratio is on one equal. The next one, the unbalanced Western happens when the resistance ratio don't match, creating a voltage difference. So this we have explain about unbalanced and also balanced whetstone bridge when the sensitive ratio in one leg equals in another. So we're going to go look through the working principle. So this is the working principle of our strain gauge, this one. So this is the, so we have, we have four resistor R1, R2, R3, R4. So the supply voltage is VCC divided by V in. V in means V input is applied across the bridge, which is top and also the bottom part. So the meter is also okay. So can you see the left pair we have R1 and also R2. So R1 R2 will create one middle point of voltage, and the right pair we have R4 R3, it's also create another midpoint of voltage. So this meter measure the difference between these two midpoints. So here is where we will measure our voltage. We will go through that one more detail in our next task, which is task number 2, by looking how the meter will be measured in between these two midpoint of voltage. So this is our task 2, which is sensor circuit design. So our sensor circuit design, now I'm going to explain. The first part is our straight gauge with whetstone bridge. So this is our multi-stream design. Okay, the multi-stream one, you can see, as I said, we have R1, R2, R3, R4. So this is where I say the meter will be measured at R2, and also at between R1 and R2, and also between R4 and R3. This is where we will measure our voltage, these two middle point. This is the multi-sim part, and this part is the sketching part lah. Okay, this is our sketch. In multi-sim, it's very hard to draw like this, because we cannot turn the resistor this type. We only can turn to 90 degree only, or a straight. We cannot turn into like this type. Okay, so this is how we sketch. So we sketch one also, you can see this is R1, R2, R3, R4. So as we know, the output V out is measured between the left point and also the right point. If you can't understand from here, you can see this output is measured from the left point here and also from the right point here. Okay, so this is how it works lah. So we have explained this. So next sensor we're going to go is LVDT. Okay, we're going to go for our next part is our LVDT. LVDT. So LVDT, this is our multi-sim one. So we have V1, which is we are using 5 VRMS, which is AC source. Okay, this is the excitation voltage applied in the primary coil of the LVDT, and we have L1, L2, which is 12 milli inductors. Okay, so we have 12. This one represent two secondary coil on either sides of the primary and coil. Primary coil, we cannot draw the actual diagram like this in our multi-sim. So in multi-sim, we manipulate like this. Okay, we imagine in this type of circuit. So R1 and R2 will represent 1 kilo. It's actually 1 kilo ohm resistor. It's actually represent the load of circuit, resistance connected to each secondary coil. Okay, so so then we use multimeter to measure the output voltage at the left and also at the right, which is at V1 and V2 of the secondary coil. So again, I explain, V1 is actually our excitation voltage applied in the primary coil. Okay, this is 5 VRMS. L1, L2 is actually this one. This is L1, this is L2. It represents two secondary coil, either of the on either side of the primary coil. R1 and R2 is actually represent the load of circles which is connected into each secondary coil. Okay, so this is our actual diagram lah. Okay, this is from the sketching one. So the sketching one also, you can see the same thing. The primary winding is actually in the middle and also existing by the AC source. Okay, VP is actually the AC source. So two secondary winding, okay, two secondary winding S1 and also S2, can you see, is connected into the opposite direction, which is we call it as a series opposition. Okay, so movable coil, so this one will move as I explained just now in the working flow in our previous slide lah. Okay, the working principle of LVDT. Okay, inductive variable displacement transducer. Okay, So this one, can you see by our this one? So the next part is we're going to explain about capacities displacement sensor. Okay, this is our next sensor. Okay, so this sensor, this capacity sensor is basically two sensor plate which you have top and also we have in bottom. So you will explain the multisim part. So we use RC circuit to represent the capacitance change. As we know, again, we cannot design the actual circuit of like this in our multisim. So we do like this to represent our capacities displacement sensor circuit. So as we know, V1 is our AC source. Okay, V1 is our AC source, provides an AC signal. Okay, C1 is 100 NF. Okay, this is our C1. This is the capacitor sensors represent the plates. Okay, and R1 is 10 kilo ohm, which will act as a resistor to form an RC network with the capacitor. So we use oscilloscope to measure the output waveform or to measure the voltage. So the how it works also I've explained just now. When the displacement happens, the capacitance exchanges because the capacitor is a RC circuit. The changing capacitor changes the voltage across the resistor. So this is the voltage across the resistor, and also change just the output signal seen on the oscilloscope. So in short terms, we can understand that even the movement changes capacitance, it's also changed the electrical signal, and that is what you measure, that is as a displacement. So this is the multisim part. Okay, and this is the sketching part. Okay, this is the sketching part. So as you can see, this is the sketching part. So the sensor is actually basically of the two capacitor plate, which is top and bottom. This is the distance, d over 2. As I explained in the formula, we have the formula d below is 2. So then this is the the part the part that it marks X is actually the moving object or the moving plate. So when it moves, the gap distance between these two plate will move together, as shown as over here lah, as I shown over here. So changing the gap changes the capacitance. Okay, so this is the sketch part. So that's all for today's slide. So next, I will proceed to my next team members for the task 3 and the following tasks required. Thank you so much.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir Husni bin Asli. My matrix number is B1224107757. Today I'm going to present about assignment 1, instrumentation and measurement. So for my part, I'm doing task 4 and task 5. Okay, first I'm going to talk about task 4, sensor characteristic. So we are doing sensor. I'm gonna choose three characteristics. One is sensor sensitivity, sensor linearity, and sensor temperature effects. Okay, first for sensor sensitivity, what is sensitivity? It is refers to change in output signal, the unit change in the measured physical quantity. So for strain gauge, the sensitivity is relatively low because strain causes only a very small change in resistance. Therefore, the output voltage is typically in the millivolt range and requires amplification. Next, for capacitive sensor, the second sensor, uh, sensitivity is high when the plate separation is small, as small displacements produce noticeable change in capacitance and output voltage. And for the LVDT sensor, inductive sensor, the LVDT has high sensitivity due to its differential output. Small core displacement produce measurable voltage difference between the secondary coils. Okay, that's for the sensitivity part. Next is the linearity part. What is linearity? It is describes how closely the sensor output follows a straight line relationship with the input physical quantity. So for the strain gauge, it exhibits good linearity within its elastic deformation range. Beyond this range, non-linearity may occur due to material properties. Next, for capacitive sensor, the relationship between capacitance and displacement is nonlinear, especially when the plate saturation change significantly. And for the LVDT inductive sensor, the LVDT is highly linear around the null position, making it suitable for precise displacement measurement. And lastly, for task 4, the temperature effects. Temperature effects occur when changes in temperature alter the sensor parameters. For the strain gauge, temperature can change or can affect resistance, causing measurement drift. Self-heating due to current flow may introduce error. Next, for capacitive sensor, temperature can also cause physical expansion of plates, slightly changing capacitance. And lastly, for LVDT inductive sensor, temperature change may affect coil resistance but has a bit minimal impact on inductance, making LVDTs relatively temperature stable. Okay, that's all for task 4, sensor characteristic, and I'm gonna go for task 5 for application scenario or the real world application. Okay, for strain gauge sensor, we can use it in load cell in an electronic weighing scale. A strain gauge is suitable because it can accurately measure small deformations caused by weight. When a load is applied, the resistance of the strain gauge changes, producing a voltage output that is proportional to the applied force. This makes it ideal for weight and force measurement system. For capacitive sensor, we can use it in touch sensor use in smartphones or control panel. The capacitive sensors can detect changes in capacitance caused by a finger or object near the sensor. They are fast, reliable, and have no mechanical contact, making them suitable for touch-based and proximity application. And lastly, LVDT for inductive sensor. We can use it in position measurement in industrial machinery. LVDT sensors are suitable because they provide accurate and linear displacement measurement. They have high reliability and long lifespan since there is no physical contact between the core and the coil. Okay, that's all from me. Sekian, terima kasih.
Assalamualaikum. Nama saya Muhammad Harith. Saya akan bentangkan tentang task 3 output analysis dan calculation, iaitu resistive strain gauge. Sebelah kiri ada output calculation, iaitu pada balance dia akan sama dengan R1 sama dengan R2 sama dengan R3 dan sama dengan R4 dan akan sama dengan R. Bila strain dia apply akan sama dengan delta R untuk output voltage of bridge. V0 sama dengan Vs kurungan R tambah delta R per dengan 2R tambah delta R. Sebenarnya akan tolak dengan R per 2R. Untuk small strain, V0 sama dengan kurungan delta R per dengan 4R darab dengan V supply. Untuk output calculation dia, saya ada letak contoh calculation nya, iaitu V supply sama dengan 5 volt. Resistornya adalah 120 ohm. Untuk small strain, delta R nanti adalah 0.5 ohm. Untuk V0 je 0.5 ohm per dengan 4 kali R iaitu 4 kurungan 120 ohm kurungan darab dengan V supply. V0 ni sama dengan 5.2 mV. Untuk large strain, delta R sama dengan 1 ohm. V0 sama dengan kurungan 1 ohm per dengan 4 kali R, 4 kurungan 120 ohm kurungan darab 5 volt. V0 sebenarnya sama dengan 10.4 mV. Untuk penerangan, an increase in mechanical strain increase the resistance of strain gauge which unbalance the Wheatstone bridge and produce a proportional increase in output voltage. Seterusnya adalah capacity sensor, output equation, capacitor reactors at C sama dengan 1/2 pi FC, output voltage sama dengan V naught Vs darab R kuasa 2 tambah capacity reactors kuasa 2, lepas tu square rootkan dia. Sebelah kanan ada contoh calculation untuk penerangan dia. Reducing the distance between the capacitor plate increase the capacitance which decrease capacity reactance and result in higher output voltage. Untuk terakhir, linear variable differential transformer ataupun pendeknya LVDT. Output equation ni V naught sama dengan V1 tolak V2 untuk inductance reactance XL 2 pi FL. Sebelah kanan ada contoh pengiraan dan penerangan dia adalah displacement of LVDT coil change the inductance of the secondary coil producing a differential output voltage proportional to the magnitude and direction of displacement. For conclusion, all three sensors demonstrate a clear relationship between physical input and electrical output, strain, cause, resistance change, displacement, alter capacitance, and common modified inductance, resulting in measurable output signal. Okay, terima kasih.